We plan to use the trapezoidal rule to estimate the integral from -1 to +1 of 3 cosine squared of 2x minus 5 dx. Find the smallest number n of strips for which the error ET is guaranteed to be at most 10 to the -4, which is 1 over 10,000, or 0.0001. And you may use the error bound, like ET is less than or equal to mb minus a cubed over 12n squared, where the second derivative is bounded by m. Okay, so we have some options: 50, 100, 200, 400, or 800. All right. And by the way, this is adapted from an old exam. So this is the kind of problem that we would ask, or that we could ask. Do we have an answer? C? C is a good guess. D. What? D. D is also a good guess, because D is right. That's the best guess, right? All right, good, D. And C is close, and we might talk about why you might be tempted for some of these options here. Okay, so we have our pieces m, b minus a, and n. Now we're trying to figure out n. So we say, well, we have information about how much we want our error, which more or less tells us something in this direction. B minus a, that's a freebie, because we're going from -1 to 1. So b minus a is 1 subtract -1, which becomes 2. So really, most of the time when we work through those error bounds, we got to put some energy into m. Now, sometimes they give us m for free, but sometimes we have to work for it. And we say, well, m comes from understanding the second derivative. So we say, okay, let's dig into that second derivative. And, well, all right, we have our function, but our function involves a square, 3 cosine squared of 2x minus 5. And we say, well, it'd be nice if it didn't involve a square. Well, we have ways to do that. Power reduction. You know, use your formulas. Think about how to make things simpler. Now, why would we want to do that? Well, it's going to make simple derivatives. Just like using power reduction makes simple antiderivatives, it can be useful to make simple derivatives. And so we say, all right, we can really think of our function as 3/2 plus 3/2 cosine of 4x minus 10. Start taking derivatives. And every time we take a derivative, don't forget to pull out a 4. So where did this -6 come from? Well, it's 3/2 times 4. The reason it's negative is the derivative of cosine is negative sine. That's the first derivative. Do it again. Derivative of sine will be cosine. Pull out another 4. We get -24. And we say, well, second derivative, because you see cosine, one nice thing to remember about cosine and about sine is that they're bounded. They never go above 1. They never go below -1. So we can use that information to control the size. So that tells us that the m we should be using is 24. So we say, all right, plug in what we have. 24, 1 minus 1 cubed over 12n squared. If we clean it up, that becomes 16 over n squared. Now, depending upon the rules that you did for derivatives, if you forgot to bring out the 4, for instance, you'll get a slightly different constant, which might lead you to a different answer. So be careful. Now we say, well, what do we want? If we can make 16 over n squared small, we win. So that's our goal. 16 over n squared is less than or equal to the number we're after. Flip both sides. Flip the inequality. Take square roots of both sides. N over 4 needs to be greater than or equal to 100. So that leads us to the conclusion we want n to be at least 400. And you might notice we phrased it very carefully. Because you might, if we had said something like, find the number n of strips for which the error is guaranteed to be at most such a thing, then you should say, well, just go for the biggest number. It's got to be right. That's why we said the smallest that we're guaranteed. Because otherwise, you know, anything above 400 is also guaranteed to work. And so we have to be careful how we phrase things. All right. Any questions? Well, our thought for today comes from Pele, great soccer player. And success is no accident. It is hard work, perseverance, learning, studying, sacrifice, and most of all, love of what you are doing or learning to do. And I hope you grow. Maybe love might be a very strong word to say, I love Calc 2, but at least I hope you grow to like it. And I think you have to work at it. Success definitely doesn't just sort of drop out of the sky. It takes work, it takes time, and you have to keep at it. You have to keep at it. All right. Well, what's our goal for today? Very simple. We need to talk about improper integrals. Improper integrals, integrals involving infinity. Now, in terms of like specifically for our formula sheet, there's nothing on our formula sheet dealing specifically with improper integrals. So this is just, we have to understand these procedures. Improper integrals can show up in partial fractions. It can show up in trig substitution. It can show up basically anywhere. So as a reminder, we finished last time with this slide. And we said, okay, improper integrals, an infinity is involved. And infinity is weird. You have to be careful. The problem with infinity is it's one of those things, it's not a number per se. It's sort of this concept, arbitrarily large. And so we can't really plug in infinity. We often say that, plug in infinity. We have to put it in quotes, plug in infinity. But what we can do is we can say, well, what would happen or what should happen? And so when we start getting infinities involved, we have to be careful and we start having to ask the question, what should happen? And as a reminder, when we talk about what should happen, that leads us to limits. Now last time we mentioned limits and a lot of people are like, ooh, there was definitely a reaction. And I think I know what it is. You're like wondering, are we going to get to do Le Hôpital? Is he going to go, Yes, it can happen. And hopefully we get to the point today where it does happen. So, okay, exciting times, exciting times. Just when you thought you were done with the silliness pulls you back in. All right, so how can an integral involve infinity? Well, there's two ways it can show up. One is the function is blowing up, so vertical asymptotes. And usually it's caused by a division by 0. Now, when we talk about the function blowing up, we don't care if the function blows up away from where we're integrating. We only care about it over the interval in which we're integrating, including the endpoints. Okay, so that's number one. Number two, we could have a horizontal asymptote. Now, in that case, what I'm talking about is that the bounds could involve infinity or minus infinity. And of course, the third thing is you might have both happening in a single integral. And so it's quite possible you have multiple problems for one integral. All right, so let's think about this. I have some example of integrals, and let's think about what's going on. So we have sort of two categories. We'll have category 1 and category 2. We'll mark these here. Let's go through and talk about them. All right, so for the first integral, is it a category 1 or a category 2? Is there a vertical asymptote or is there a horizontal asymptote? Or is there both? Now the horizontal is really quick to spot, right? In fact, we can mark all the horizontal ones right away. What are we looking for? Infinity in the bound. So you say, okay, there's an infinity, there's an infinity, there's an infinity, and there's an infinity. So these are all the ones where we have infinity in the bounds. So those are the easier ones to spot. But let's look at these. Vertical asymptotes. What are you looking for? Usually divide by 0. Okay. Do we have a divide by 0 somewhere from 0 to infinity? Okay, where? 0. So 0 is a problem. Okay, so there's 2 problems here, and they're different types. Does this one have a divide by 0 problem? It does for a function, but does it for the integral? So where's the divide by 0 happening? At 0. Do we care about what happens at 0 for this integral? No, because 0's far away. And you might think, is 0 that far away from 1? Yes! That's very far for calculus. You know, calculus is very, if you're not right there, you're far away. So this is actually okay. No problems on this one. We don't have to do anything. All right, how about this one? Integral negative 1 to 1, 1 over square root of 1 minus t squared. Does this have any divide by 0 problems?
Yes.
Where? At 0?
Oh, wait, no, at 1.
At 1?
Negative. At 1.
Anywhere else? And negative 1. So there's actually problems at both endpoints, so we'd have to deal with 2 issues. How about here? 1 over the cubed root of y squared dy. At 0. Now here, if we compare the previous one to this one, you'll notice our problems were at the endpoints. Here the problem is in the middle. So you have to be open. It could be either case, either at the endpoints or in the middle. And how about this one? Any issues?
No.
1 over x squared plus 1 is, do we have any divide by 0 kind of issues? Now you might be like, oh, I want to make this thing complex. What about I, Steve? No, that's not this class. That's a different class. We're okay. We didn't do e to the negative x. Does e to the negative x ever have issues? Well, e to the negative x is like 1 over e to the x. So yeah, okay, so it has a problem when e to the x is 0. And e to the x is 0? Never. Never. So e to the negative x, no problems. 1 over x cubed plus 1? Does that have any issues? Where's the issue? Negative 1. Okay. So anyways, the point is we can have problems. So be ready to look for them. Like I said, the second case, horizontal asymptotes, always easy to spot. The other case, whenever you have fractions, you should always do a sort of a quick mental thing. Hey, do I ever divide by a 0? If so, be ready. Be ready. All right. So, how do we actually handle these? Well, we want to answer what should happen. So let's channel our inner Calc 1 student. And we would be faced with situations like 0 over 0. We said, well, we can't handle 0 over 0. But what we can do is we can look nearby and move a little bit away from the 0 over 0 and say, what's happening nearby? And then move in closer. We're going to do that exact same idea. That's how we answer what should happen. So the first few steps are setting things up. We look for the infinities. Where are they? Are they at endpoints? Are they in the middle? Do we have vertical asymptotes? Make sure you know where your infinities are. Now, after you've done that, break the integral into parts. And essentially, one part for each infinity. So in other words, we don't want to have multiple problems in one integral. So if you have multiple things blowing up, or maybe you have a divide by 0 at the origin and you're going off to infinity, split it up so that each integral by itself has only one issue. And not only does it have an issue, it happens at the endpoint. So break up your integral based on where your problems are. All right. Now, the next part. For each part, we're going to estimate the value of the integral by saying, well, the problem is at the endpoint, so we're going to move off the endpoint a little bit. And if we move off the endpoint a little bit, then we're okay. It's a perfectly fine integral because there's no infinity involved. And you might say, well, wait, how do you move a little bit off infinity? Well, just pick a big number like 3 or 4. Those are big. They're close to infinity. Well, as close as any other number is to infinity. But the moral here is move off, and now the magic. Take the limit as b moves to the endpoint. And I should be very specific here because I forgot to write it down. Oh, I did write it down. Okay, one-sided. Phew. I thought I forgot it. One-sided. One-sided limits. And because we don't want to have an issue where that looks like I'm crossing it out. I'm supposed to be highlighting it. Oh my goodness, orange on orange is not a good idea. One-sided. So if the value converges, great. That means that the integral works. So even though there's an infinity involved, life is good. We made it work. And we've seen in Calc 1, we've seen cases where we can head off to infinity and still get a finite value. So it's okay if things work. So we move on and we say, well, we might have other integrals we have to work through. Because remember, we split it up. And we're going to do this for each integral. And then at the end, we put it together. Now, if any part broke down, we say, okay, we stop, it doesn't work, it blows up, game over. Doesn't converge. If all parts worked, we say, wonderful, then the whole integral converges, add up the parts, life is good. And we're ready to go. And as we mentioned before, l'hôpital, well, l'hôpital can come into play when you're dealing with limits because you might have things where you have 0 over 0 or infinity over infinity. All right, so that's our idea. Break into parts, handle each part separately, put it back together. It's not that bad. Any questions? All right. Well, let's start with a quick question. Why do we insist on breaking into parts? Why not just handle everything simultaneously? Well, so let's look at the following situation. We're going to calculate the integral from negative infinity to positive infinity of 2x over x squared plus 1 in two different ways. We're going to argue, hey, let's do it by handling both infinities at the same time. And in one case, we're going to go from negative b to positive b. And of course, as b gets big, it goes from negative big number to positive big number. And so, okay, that catches everything. So let's do that case really quickly. And I don't want to dwell too long on the integration here. Do we know how to integrate 2x over x squared plus 1? Does it look like something we should be able to integrate? Okay, someone's recommended u sub. What would you u sub? If we substitute x squared plus 1, what's the derivative of x squared plus 1? 2x dx. So it's like a 1 over u. Integral of 1 over u? Log u. Yeah, so this becomes natural log u, x squared plus 1, evaluated from negative b to positive b. So that's natural log of b squared plus 1, because I'm plugging in b. Subtract natural log of b squared plus 1, which is 0. And now that I've written all this out, I realize I did something very silly, and I would have lost a point if we didn't correct it. So I want to make sure I get my points. Got to get them all. What have I forgotten to write down? Yeah. You got to carry that notation through until you actually do the limit. So there's a limit here as b goes to infinity. Limit as b goes to infinity. Limit as b goes to infinity. Okay, so what is the limit as b goes to infinity of 0? I know, it's like, he's really testing us. It's been like a whole semester since we did limits. So as b gets close to infinity, 0 gets close to 0. All right. So the answer is 0. Nice. Ha ha. Of course it is. How could it be anything but? So clearly we're going to get 0 again. Well, this time I won't forget to write limits. Limit as b goes to infinity. We already talked about the integral, same integral, x squared plus 1 from negative b to 2b. That's the limit as b goes to infinity of, when we plug in 2b, log of 2b quantity squared would be 4b squared plus 1, subtract log of b squared plus 1. Now here we have a log minus a log. When we have log minus log, what can we do? Yeah, it becomes division. So this is our limit as b goes to infinity, log of 4b squared plus 1 over b squared plus 1. And the nice thing is you can push the limit through the log. The reason you can do this is log is a continuous function. And limits and continuous functions get along well with each other. So this is log of the limit as b goes to infinity, 4b squared plus 1 over b squared plus 1. What is this doing? 4b squared plus 1 over b squared plus 1. b is a big number. What does this do? And why does it do it? So when you have fractions, focus on the big parts. The small parts won't matter because the big parts are going to dominate. B squared and 4b squared versus the ones. Are the ones going to make a big difference when we start talking like b is a million? No. So we say, okay, ignore the lower order terms. What's happening? 4b squared over b squared. What is that? 4. So this goes to 4. So what we have is log of 4. Now, we may not know a lot about log of 4, but there is one thing we do know, is it's not 0. So what have we done here? We did the integral from negative infinity to infinity. We did it in 2 different ways. We got 2 different answers. How is that possible? What's going on? It seems to be breaking our rules. Well, if you sketch 2x over x squared plus 1, one thing you'll notice is that this function, it's a somewhat peculiar function. Very weird, unusual, not what you'd normally see. Some people might even say that this function, 2x over x squared plus 1, is odd. It's an odd function. And if you graph it, it's positive on this side, negative on this side. And there's this beautiful symmetry. Here's what's going on. You have this right half, and you have this left half. And in the right half, the amount of area on this side is plus infinity. In this left half, it's minus infinity. So when you put them together, we're getting infinity minus infinity. And what is infinity minus infinity? Good, that's a good answer. Infinity minus infinity is ambiguous. It has no meaning. It can, in theory, be anything. And sometimes when we use limits, we're able to say, oh, it is this, but in other cases, you cannot put anything on it. And we're going to see examples of this later on in the next part of the course, where it's like, oh, weird things are going to happen. Things that we thought are fundamentally true are going to be messed with. But, well, that's for the next part of the course. Okay, so This will be a very useful fact we'll get to in a minute. Let's do the integral of 1 over x to the p dx. All right. And we're going from a to infinity. A can be any number. If you like, just think of a as 1. So how do you integrate 1 over x to the p? I mean, hopefully this is not so bad. We've seen this integral before. It's one of those Calc 1 type integrals. Any thoughts? Now you might be thinking, oh, Steve, you got to be careful here because you didn't tell us what p is. You're right, I didn't tell you what p is. P is some number. So it depends on your choice of p. So let's just say p is some arbitrary number and work through it from that perspective. Now that I've said it's some arbitrary number, some arbitrary numbers are more arbitrary than others. Is there any very particular choice of p which behaves a little differently than all the other choices for p? All right, someone's holding up their finger here. To be clear, it's not the middle finger. I'm not in trouble. And okay, 1. There's a very special value. Okay, so let's break this into two cases, which is we'll have p equals 1. So we have the integral a to infinity of 1 over x. And then we'll have p not 1, which is the integral a to infinity of 1 over x to p, which we'll write as x to the minus p, because that's a more calculus-friendly way to write things. All right, so we're going to do it in two cases. So let's talk about the p equals 1. So we're going to work it out down here. We have this integral. It's an improper integral. Why is it improper? Because we're talking about it today. No, because we have the infinity up in the bounds. We don't have the vertical asymptote because we said a is positive. We're away from 0, so only the infinity in the bounds. So to deal with it, we're going to write this as the limit as we get close to infinity of the integral a to b of 1 over x dx. So what's the integral of 1 over x? Natural log. Evaluate from a to b. So this is the limit as b goes to infinity. Log b minus log a. Now log a is fixed. That's not changing. The b is what's changing. What happens to log as you head off to infinity? It goes to infinity. It takes its time. It's kicking and screaming, I don't want to go to infinity. But it gets there. It gets there. It gets there super slowly, but it gets there. So this heads off to infinity. So it's diverging. All right. So p equals 1 is bad. Well, now let's do p not equal 1. All right, but we still have the same issue. We have that upper bound. So we're going to do limit as b goes to infinity, a to b, x to the minus p dx. All right, so given that p is not 1, how do you integrate such a thing? What's the rule? X to a power, what do you do? Add 1 upstairs, divide by your new power. So add 1 upstairs, 1 minus p, plus 1 minus p, divided by 1 minus p. We're not dividing by 0 because p is not 1, from a to b. which is the limit as b goes to infinity, of b to the power of 1 minus p divided by 1 minus p minus a to the 1 minus p divided by 1 minus p. Now, the a term is fine. We don't worry about this. This is fixed. It's a number, so it's a fixed number. Focus on the term with the b. That's the part that's changing. What's going to happen to this? Well, maybe. It depends on this number upstairs. If this number upstairs is positive, what's going to happen? Get big number to a positive exponent means what? We're getting big. What if the thing upstairs is negative? Big number to a negative exponent. What does that tell you? We're getting small. Because negative exponent means you have something big downstairs. So this actually breaks into two cases. So let's figure this out. When would 1 minus p be positive? So if p is less than 1, 1 minus p is positive, right? Because you can just imagine 1 minus p positive. This goes to infinity, diverges. If p is greater than 1, then we have a negative exponent. This part goes to 0, and what will happen is we go to this negative a 1 minus p over 1 minus p, which is a terrible expression, but the key here is that this converges. Here's the punchline. The thing that we should take away from all of this, and this will be a very useful fact, maybe today, maybe next time, we'll see how quickly we get through the rest of this, is that the integral a to infinity of 1 over x to the p dx converges, in other words, it's finite, if and only if, what's true? For which values of p does this converge? If p is less than 1, diverges. If p is 1, diverges. So when does it converge? Yeah, p is greater than 1. So this is a very simple integral, but we will get a lot of mileage out of this fact. So 1 over x to the p dx, that integral, converges if and only if p is above 1. All right. Any questions? Essentially, you can think of it as that 1 over x is right on the border. It's right in the middle. It really wants to converge, but it just barely misses out.
So I guess eventually we could just like see the equation be like, oh hey, it converges eventually.
Well, we're going to get to the point, and as I said, hopefully today, where we're going to change our question. Maybe not today, but hopefully, which is a question of, does this integral have a finite value or does it not have a finite value? Sometimes we don't actually care about knowing the exact value. We just care to know, is there a value? But that's for later on. All right, so here's another problem. Given that this integral, x squared e to the negative x dx is negative x squared plus 2x plus 2 e to the negative x, and I forgot to write down plus c, but that's all right. Now I've remembered it, plus c. So we have this integral. Find the integral from 0 to infinity of x squared e to the negative x dx. All right, what kind of integral do we have?
Improper.
It's improper because we have infinity. All right. So, what happens here? Well, we say if we want to know this, we'll take a limit as b goes to infinity, and not every improper integral involves infinity, but it's good to start there. 0 to b of x squared e to negative x dx. All right. Do we know how to integrate x squared e to the negative x? Yeah, because we read what's written right above it. Now, what if we didn't have something written right above it? What would we do? Do we know how to integrate this? What's the technique?
By parts.
Integration by parts. So if you did integration by parts a couple times, you'd get the integral. But for us, in the interest of time, they said, hey, figure this out. Limit as b goes to infinity of minus x squared plus 2x plus 2 e to the negative x. And then we're going to evaluate from 0 up to b. All right. Well, this becomes our limit as b goes to infinity. And we plug in everywhere we see x, we plug in b, so minus b squared plus 2b plus 2 e to the negative b. Subtract. Everywhere we see x, you plug in 0. Well, we get 0, 0, a 2. Don't forget about that minus, so minus 2. And e to the 0 is 1. All right. Well, what to do, what to do? One nice thing is this part on the end isn't changing. It's always 2. So we can pull that out. We'll just pull that out to the front and say it is what it is, and we have the rest of it. And let's go ahead and write it as not 2 plus, but 2 minus. We'll use that minus there. Now, looking at what we have this b squared plus 2b plus 2 times e to the minus b. What's happening to b squared plus 2b plus 2 as b gets big, as we are getting close to infinity? What's happening to it? It's getting big, going to infinity. What's happening to e to the negative b? It gets small, goes to 0. So it's going to like infinity times 0. And infinity times 0 means more work. More work. Now, of course, how do we make more work? Well, we prefer fractions. So we can take advantage of the fact that there's e to the minus b means really e to the b downstairs. Now, instead of going to infinity times 0, it's doing what? It's going to upstairs, infinity, downstairs, infinity. Infinity over infinity. Ah, mon ami. We have a way. Le hôpital. When we see infinity over infinity, we can use le hôpital. Le hôpital. What a great thing. It's been too long. All right, so we're going to apply le hôpital. We put a little marker here. I like to just indicate this is because of le hôpital. Make sure you have this acknowledgement. It's like, oh, I'm definitely doing this because there's an infinity over infinity going on. All right, so this becomes 2 minus. All right. Do we remember le hôpital? What do we do with le hôpital? It's a fun way to take derivatives of a fraction. Yeah, you take the derivative of the top and you take the derivative of the bottom. It's not a quotient rule. Oh, okay. Derivative of the top, 2b plus 2. Derivative of the bottom, e to the b. And what does this do? This goes to infinity over infinity, which means more work. Le hôpital. Oh, le hôpital. Because it's been too long. We can't just do it once. We got to do it twice. We got to make up for lost time. All right, limit as b goes to infinity. What's upstairs? 2. What's downstairs? E to the b. What does that do? It goes like 2 over infinity. But 2 over infinity, actually, we know how to handle that. 0. So this part goes to 0, meaning the whole thing is 2. Because we had that 2 out in front. All right. So shifting gears, we can talk about comparison tests. Now, the goal of comparison tests is not saying find the value of the integral. The goal of the comparison test is to say, does the integral have a value? In other words, does it blow up, or does it have a finite answer? And so it's a different kind of problem, and so we kind of have to look at it in a different way. In some sense, it might be a little bit easier, because again, we're not after a specific value. So our basic question is yes or no. Does it converge, get a finite value? No, we diverge. And we have a very simple observation. We learned this in Calc 1. If we have nice continuous functions, and let's say that f of x is between 0 and g of x, then if we integrate over some interval from a to b, then 0 is less than or equal to the integral from a to b of f of x, and that's less than or equal to the integral from a to b of g of x. And that's not hard to see why. If your function's bigger, you should have a bigger total. If your function's smaller, you should have a smaller total. Now, what can we say? Well, let's suppose g of x converges. That says g of x is small. If I am something smaller than small, what is true? If I'm smaller than something small, I must also be what? I'm also small. So if I'm below something which converges, I have to converge. But what if we flipped it? What if we say integral of f of x diverges? Now that says that thing is big. If I'm bigger than something big, what am I? I'm also big. So if I'm above something which diverges, I must diverge. So I can try to say, well, I might be a complicated integral, but how do I compare it to something simpler? So that's how we're looking. Now, be careful, there are things that we can't conclude. If the integral of g of x diverges, what does that tell us about the integral of f of x? If this integral is big, what do we know about this integral? Nothing. We know nothing. It could diverge, it could converge. So be careful. Basic rule of thumb, I'm smaller than something which converges, I'm great. I'm bigger than something which diverges, I'm great. Otherwise, I don't have any information. All right. So, does the integral from 1 to infinity of 2 plus sine x over x converge? Yes, no question. What do we think? Yes or no?
I feel yes.
So usually we answer the question before we do the work. What does it kind of look like? The sine x does what? It moves up and down, but it doesn't move up and down by much. So basically it's like a number. So what does this look like? It looks a lot like something over x. Does 1 over x converge? No, that's one of the things we figured out. 1 over x won't converge. So we say, okay, we think the answer is no. So now we have to justify the answer. So if we think the answer is no, we want to get this bigger than something which we know diverges. So we say to ourselves, well, we want something here that's bad. So let's think about what we can do. The over x we like. What can we do with the 2 plus sine x? 2 plus sine x is bigger than or equal to what? I know, I'm testing you on your knowledge of sine today. 1. Where does that 1 come from? Well, sine x can go from where to where? Positive 1 at the top, negative 1 at the bottom. So the smallest 2 plus sine x can ever get is 1. All right. This integral diverges when we talk about the integral from 1 to infinity. So that implies that when we look at this integral, that this diverges. So by putting this 2 plus sine x over x above something which diverges, we know that integral diverges. This integral, does 2 plus sine x over x squared converge or diverge?
Like this. I mean, if he was 2 last time, that conversion. Could you play this? I feel like
So it looks like what's downstairs? X squared. Think about integral of 1 over x squared. Does that converge or diverge? It converges, right? That goes back to the integral of 1 over x to the p. So we think about, okay, so now our goal is not to get something below that diverges. Our goal is to get something above that converges. What's true about 2 plus sine x? Two plus sine x is how big can it get?
3.
3. Because sine x can get at most 1. The 2 plus sine x can get at most 3. So this integral, this converges. That implies that this integral, which is below it, still is above 0, but that implies that this must also converge. So we found something bigger than it which converges, so it must converge. Just as over here, we found something smaller than it which diverges, so it must also diverge. Well, this is a lot of fun, but unfortunately we have to stop here.